Okay, so now on this one, I wanted to be able to show you what the heck this problem is talking about, hence the webcam. So this says a metal worker wants to make an open box from a 12 by 16 inch sheet of metal. And he's going to do this by cutting squares from each corner. So essentially, he's going to have something like a rectangle with squares cut out of each corner. And he's making an open box, so that's just going to be a box without a lid, by folding up the sides. So hopefully you can kind of see how this could be a box if I folded up all of the sides. I don't know how great of a job my webcam is doing at capturing this, but this is what the box would look like if all the sides cooperated. Then it would be a box. So first I want you to write an expression for length, width, and height of the open box. So what I'm going to do first is kind of like draw out this scenario. So we had a rectangle, and then you're cutting corners from each side. But we don't know like how much we're cutting from each side. So the sides of these squares are going to be considered X long. And that's for like all the sides of all of these squares all the way around the box in every corner. So we need an expression for length, width, and height. So our original length, which is this whole part here, the original was 16 and the original width was 12. So my length now, since I cut corners out of both sides, is going to be 16 minus the amount that I cut out. And so the amount that we're cutting out is X, but then since we're cutting it out of both sides, we're going to say that's 2X. So our length is going to be 16 minus that amount that we're cutting out of both sides. So minus 2X. And then our width, it used to be 12, but we're cutting 2X out of it as well, right there where I just shaded. So it'd be 12 minus 2X. And then our height, if you look at my makeshift box again, then the height is the amount that we're able to fold up. So the amount that's being folded up here is going to be the same amount that you're cutting out on the corners. So the height is just going to be X itself. So height equals X. So then we want to write a function for volume for that. So the volume of a box like this is going to be the length times the width times the height. So our function for volume is going to be 16 minus 2x times the width, which is 12 minus 2x, times the height, which is just x. And then in part C, it wants us to graph that and find the maximum volume that can be contained by the box. So to graph it, we're going to go to Desmos. So let me get that pulled up. Okay, so I pulled up Desmos and I went ahead and typed in our function as well of 16 minus 2x, 12 minus 2x times x. And right now we can't see where the maximum is, so we're just going to have to zoom out until we can see it. I'm just going to scroll up a little bit too. And the maximum is way up here at 2.263 and 194.067. So if we go back to see what the question was asking for, we want to know the maximum volume that can be contained by the box and the size of the square. So if I come down here, then the size of the square is going to be x, and that was 2.263, and I think this was in inches. So yeah, it's in inches. So the size square that we're going to want to cut out is 2.263 inches. And then the maximum volume is whatever my y value was. So if I go back, then my y value was 194.067. So the volume was 194.067, and that would be in inches cubed, would be the units on that one. And then we're just going to do one more example. So this one's for an in-ground pool, which is another situation where you have a little open box because you don't want a lid on it. And we have the width of the pool is 4 more feet than the depth, and the length is 30 feet more than the depth. So our main variable here is going to be depth, and then the 3,000 cubic feet, that's going to be representing our volume. So our volume in this one, it's length times width, and then it would be times height, but since it's an in-ground pool, it's going down instead of up, so it's going to be the depth. But the depth is the same measure as the height. And so our volume is length times width times depth, and so we just need to write out what each of these are. So the length of the pool, it says, is 30 more feet than the depth, so that's going to be the depth plus 30. The width of the pool is 4 more than the depth, so the depth plus 4. And then the depth is just going to be the depth. It's just going to stay itself. And we want to know the dimensions of the pool if the volume is 3,000. So I'm going to start plugging stuff in so we can get an equation here. So we would have the volume is 3,000. That's going to be equal to the length, which is d plus 30, times the width, which is d plus 4, times just the depth itself. So d. So this is the equation I'm going to need to solve for. So to do that, I'm going to put these different things in Desmos and graph. So we're going to have one y is going to equal 3,000, and our other is going to equal this equation, the d plus 30 times d plus 4 times d. And then since we know one of our y values is going to be 3,000, we also know we're going to have to zoom out a lot on this one. Okay, so to be able to see the line y equals 3,000, I had to zoom out to this point. So you can't see your actual cubic or like model here very well, but I'm gonna come up here and I'm gonna zoom in a little bit, like right around the point, and it looks something like this. So you see that there are 3 intersections at 3,000. So if I click through them, then we have options of x, which remember that x in this case was d in our original equation, so that's going to represent the depth of the pool. So the options for the depth of the pool are -23, -17, and 7.2. So if you think about it, you're not going to dive into a pool that is -23 foot deep. So the only option that's really realistic for us to use is the 7.2 for x. So we're going to come back here, and we would have the depth was 7.2, and then we need to find the length and the width as well. So the length was the depth plus 30, so 7.2 plus 30 is going to be 37.2 feet. And the width was 4 more than the depth, so 7.2 plus 4 is just going to be 11.2 feet. And this gives us all of the dimensions of the pool for this one. So that's just a few examples of like the types of word problems you may see. And there are other types as well where you just might have to plug in numbers or something like that. But I wanted to go over these few examples. The open box problems are just weird because like, unless you can actually see what is going on where we have stuff cut out of each of the corners and stuff, it doesn't make a lot of sense. So I just wanted to go over that, and hopefully that helped.